Hi everyone, welcome back to CST Quick Tips. Today we're going to be covering how to create a time-based e-field animation similar to this sort of thing. I'll just skip ahead to show you what it's going to look like. So you can see the patch resonating there, fields traveling upwards in the Z direction. So we're just going to cover how to view this sort of animation. And the reason this is useful is that you can view it from time 0, so you can see the beginning of the structure excitation, so you can kind of see wavefronts traveling through the structure here. Apologies if I keep scaling the animation, it's because it will reset it based on the current sort of resonant field activity, which is quite small to start with and then gets larger. So this sort of visualization isn't typically available if you just set up a normal e-field, because obviously that will use it will just show one 0 to 360 degrees sort of animation of the maximum field strength, which is not sometimes what you want to see. Sometimes you want to see the field decaying as it travels further away and that sort of thing. Anyway, how to set this up? Put this back to 0. So I've got a standard, really boring patch, just standard ground plane, little discrete port there. Just to mention again, I am using the student edition of CST, so I can't go past 100,000 mesh cells, which is horrendous, as I'm sure you're all aware. But this is just to show the general setup. One thing to be aware of is that if you are going to, if you're aiming to look for a number of different wavelengths throughout this simulation, so say you want to see 10, 20 wavefronts traveling away from your antenna, then one thing to be aware of is that obviously if this bounding box is small relative to your wavelength, you're not going to see many, because obviously it will reach the boundary before it's had the chance to run through a few cycles. So if I weren't using the student edition, I'd make sure that this box, if I'm interested in only the sort of direction of propagation, which in this case is positive Z, then I would come into here and make this upper Z distance massive. So say my wavelength was 10 millimeters, I'd get 15 wavefronts out of this. But obviously I'm down at about 1.6 off the top of my head, 1.5 or 6 gig. So I'm I'm not going to get many wavefronts at all, but that's just one of the limitations. So to get this sort of animation, first of all, you have to be in the time domain, because if we're dealing with time, then there's no capability in frequency domain solver to take time into account, so you obviously have to be in the time domain. You want to set up a field monitor, presumably e-field, and then in the specification come across here to time rather than frequency. Okay, so you're probably used to doing it in frequency all the time, but if we come over to time, and you can specify a start time for the animation, a step width, and an end time. The start and end time are essentially, if we come across to the excitation signals used by CST, hang on, there we go. So this is obviously the default input signal that CST uses in the time domain, and this is the output signal. So the start and end time are essentially, if you look at this, you want to be looking in anywhere in this sort of decaying region, because at this point the excitation has traveled into the structure, the patch has begun resonating, and it's transmitting essentially, or radiation is being released from the structure. So if you don't specify an end time, it will just run up to the end point of your simulation, and obviously if you're aware of the time domain settings, then the lower this value is, the longer this will run for, and the longer your animation will be. Just be aware of the file sizes, because this can actually produce quite a lot of data. So I've run into that problem before of having, I can't remember the exact figure, but it was around 120 gig of data output from this, which my department wasn't overly happy with, but there we are. So to set up this, I'll just use the field monitor I've already got set up. So I chose an e-field, obviously the time version started at 0, didn't specify an end time, so it'll run to the end of the simulation, and I reduced the step width to 0.01 of a nanosecond, and that is just to up the frame rate essentially of the field. You can set this to a less granular value, so a nanosecond or something if you want to see a quick result, but I prefer to see all the detail in there. I've also specified a subvolume because I only want to see it on this plane. So I have set it to the calculation domain, and I'm using a plane which is normal to the x-axis. So obviously the x-axis is normal across this way, but I want to see the plane there. Well, you can see the plane of the structure I'm using. And I've set the x position to 0 just to see the maximum field in the center of the patch there. And that is it. So once you run your simulation, you'll see in the 2D, 3D results an e-field folder, you'll see your result in here. It may be set to arrows, so just make sure you're on contour if that's how you want to see it. And then we can just watch it, and you'll see it's running through the steps here at the timed step width I specified, which is 0.01 of a nanosecond, and you'll see it begin to get energy into the patch essentially. So in these early stages, it's always quite interesting with resonant structures. You can see the energy beginning to ramp up, and because you've got, we haven't got sort of uniform excitation or anything like that, and there's energy only just getting into the end of the structure here. The fields are all quite messy at this point in time, and you wouldn't usually be worried about that because obviously your antenna is just going to be radiating as normal. But as time travels on, after a few nanoseconds or so, you'll begin to see the field start to establish above the patch, and I'll essentially just have to keep auto-scaling as I go because the dynamic range of these fields will change as the simulation travels onward. So we'll just let that run through for a little bit. You can begin to see this main lobe of radiation coming off here. As that's beginning to, you can see the two resonant points here and here combining above the patch and then travelling up. So there's a good lobe there, there's an even better lobe there. So you can see how that's beginning to organise itself. I've always found this quite an interesting thing to do, even if it's not necessary for the design of your structure, the design of your system or communication link. It's just quite interesting to see sometimes how these fields establish and travel. And if you've got a radiation pattern that is squinting off in one direction, say it was travelling this way, sometimes this, if it's in a large box, it's quite nice to visualise that, and sometimes you can almost see the way the fields are combining and why that's travelling up in that direction. I wouldn't necessarily use it as a design tool, but it's just quite a neat animation, I guess, to see what's happening. So you can see what's happening here. These lobes are travelling up and away, and as this patch is polarised in the Y direction, sometimes it's useful to just look at the Y component, and you can see really obvious wavefronts. So obviously here everything's polarised in, let's say, positive Y, and then in this wavefront here everything is now polarised in negative Y. So you can see the really strong polarisation of that patch element radiating upwards. So that's pretty much it for this video. Please let me know in the comments if you have any questions or suggestions for future videos. Thanks guys.